AP Physics, hey, you're back. Welcome back to some more energy. So we're going to spend some time discussing more about energy. We're going to be talking about the conservation of energy in an isolated system. Remember, in an isolated system, that means no energy is entering or leaving the system. That means in physics, there's no work that is done on the system or by the system. So we're dealing with energy that's really just changing forms in the system. Remember, when it's changing forms, it's still energy, it's just showing itself in a different way. And we can keep track of the total of that energy in the isolated system, and the total should not change. Turns out that we can have an equation to express the conservation of energy. So a nice equation for expressing conservation of energy looks like this. There are a couple terms that we will not deal with too much in our presentation today, but basically this energy equation says that the energy before something happens is equal to the energy after something happens. So it's kind of like the conservation momentum, except for we're not going to deal with a whole lot of collisions here. It's just basically saying the energy at this time is going to be equal to the total energy at a later time. So the total energy, if you add up all the energy present in the system, should not change. That's what this equation is telling us. Now we've got kinetic energy and gravitational potential energy here, or I guess kinetic energy and potential energy. And we also have this WEXT, which is basically the work. And we're not going to deal with work in this presentation because, again, work means that energy is entering or leaving the system, and we're going to deal with an isolated system today. Another term that's present is the change in thermal energy. And remember, the change in thermal energy is associated with dissipative forces like friction, and that causes atoms and molecules to move faster and is detected by temperature. Alright, so this is a nice little equation we can use. You also notice that we have a nice little graphic down here. One way to keep track of energy is with an energy bar chart. And I'll show you how that works with a specific example later on, which will make things make a little bit more sense. Before we get into talking about some specific calculations, you have to realize how to calculate two important forms of energy. To calculate the presence of energy associated with kinetic energy, the equation is 1/2 mv squared, where v is the magnitude of the velocity. To calculate gravitational potential energy, it's mass times the acceleration due to gravity times the height. And that's how you calculate the presence of energy in that form. So those are two important equations. We're going to be looking at an isolated system where the total energy of the system does not change. So the energy may transform. It might go from kinetic to potential, or it might go from potential to thermal, or kinetic to thermal. But if we took a look at the total, so if we add up all the energy associated with this in joules, we would find that that total would not change. So the system's total energy is conserved. It's simply being transformed from one form to the other. And since it's isolated, it cannot leave the system, nor could energy enter the system. An example where we have an isolated system is in a free fall. So we have a ball here that's falling, and as the ball falls, so if I were to drop it, as the ball falls, you're going to notice that the gravitational potential energy is going to decrease, right? Because the height value is getting smaller. So if I gave a height value to this guy up here, maybe it's 10 meters, now he's at the final later point in time at 5 meters, you'll certainly notice that the gravitational potential is getting smaller. So this is initially, and then a later point in time, we have less gravitational potential energy at this later point in time. Now energy has to be conserved, so the total has to remain the same. The energy can't disappear. So if there is less gravitational potential energy, that energy had to go somewhere. What does it go into? Well, it goes into kinetic energy. So it turns out the object would be moving faster at this location, which you know is the truth, right? When objects fall, they accelerate. And so clearly the object will be faster here, and now the energy is stored or shown as kinetic energy. So in a situation where you have a isolated system of a free-falling object, the gravitational potential energy is going to decrease, but the kinetic energy increases. At any point in time, if you were to add these two together, the gravitational potential plus the kinetic, you should get the same sum. You should get the same total energy. So let's look at another example. We have a pebble being tossed into the air. And we're going to show some energy bar charts to indicate what's happening with the forms of energy. So initially, the object is launched from the ground. So we're going to say, since the ground is no height, we'll call this zero gravitational potential energy. So it's launched from the ground and therefore has kinetic energy, right? Because it was given an initial velocity. But since it's launched from the ground, which we're calling zero gravitational potential energy, it has no gravitational potential energy. When it gets halfway up, remember, since it's moving to a higher height, it has more gravitational potential energy, which means that now it has less kinetic energy, because remember, the total has to remain the same. So if I were to add up these two bars, it would have to be equal to the total of this bar. When it's at the top, remember, when you have objects that go up and come back down at the top of the motion, it stops for a brief moment, so it has a velocity of 0, which means that there's no kinetic energy. Now all the energy is stored as gravitational potential. Notice how the height of this bar is the same as the height of the kinetic energy bar when it was first launched. The total energy is not changing. Then it's on its way back down, and there's a transformation from gravitational potential to kinetic until it gets back down to the ground, and now right before it hits the ground it has all kinetic energy. And notice again how the total energy is not changing. Now you might be asking, hey, how do you know where zero gravitational potential energy is? Well, it turns out it doesn't really matter, because quite frequently we're going to be curious on how gravitational potential energy is changing. And it turns out if you choose a zero gravitational potential energy at a different point than somebody else, they're going to still find the same change in gravitational potential energy regardless. So it turns out you can choose zero gravitational potential energy wherever you would like. And quite frequently we will choose a location that is convenient. So like the floor or the ground will be zero gravitational potential energy. You can choose zero gravitational potential energy wherever you would like. So as we said, with the conservation of energy, and sometimes when we just talk about kinetic and potential, this is given the category of mechanical energy. We just talked about how in an isolated system, these guys are conserved, that just changes form. So let's look at a specific calculation example to kind of get your feet wet in terms of calculations. So we've got a quarter that's dropped from a second-story window. The second-story window is 5 meters above the ground. If the quarter passes the first-story window ledge, which is 1 meter above the ground, how fast is it moving at that location? The quarter has a mass of 5.67 grams. Now, you have enough knowledge to use dynamics, so to use Newton's laws and to use motion equations to try to figure this out. But we're going to use energy instead. We're going to use the fact that this is an isolated system. As the quarter falls, the total energy of this system is not changing. It's just going from one form to another. It's going from gravitational potential energy to kinetic energy. So we can set up our equation for the conservation of energy. The initial kinetic energy plus the initial gravitational potential energy is equal to the final kinetic energy plus the final gravitational potential energy. And then we can fill in our equations. So the initial kinetic energy, since it's dropped and it has no initial velocity, would be 0. Then we can calculate the initial gravitational potential energy, which is mgyi. That's going to be equal to the mgyf, so the gravitational potential energy when it's at the window ledge of the first story window, plus the speed of that quarter when it's at the first story window. Now if I fill in the information, we've got the mass, I convert it into kilograms. We we have the acceleration due to gravity, and we have the initial height here of 5 meters. We're currently saying that the ground is 0 gravitational potential energy. That's the reference line I've chosen for this situation. On the other side of our equation, we have all of the energy information when it's at the first story window ledge. And so I plug in the mass, the acceleration due to gravity, and also 1 meter, because that's where the quarter is located when it's at the first story window ledge. And that will be the gravitational potential energy of the quarter at that location. And of course, we have to add in its kinetic energy because it's moving at this point. And now, with this equation, I should be able to figure out how fast the quarter is moving. I can solve for VF. And I can rearrange everything and solve for it, and I find that the velocity at the 1 meter mark above the ground when it's at the first story window ledge is 8.9 meters per second. And I could just use the idea of energy to figure this out. Of course, I didn't do this here, but if I wanted to, I could talk about the energy in joules, right? I could do the 5 meters times the 9.8 times the 0.00567 kilograms to get a number here. And of course, whenever you find a number from the energy equations, that number will have units of joules. So keep that in mind. All right, so I hope that gives you a nice introductory mathematical way of solving something using the conservation of energy. We'll talk about energy in class and in future presentations. All right, stay classy, AP Physics.